Good morning, everybody, and welcome to 120th Tech Talk of Tech Forum. We conduct by month two programs in a month, mostly online and sometimes at Institution of Engineers. So today we have Mr. Amitej, who is going to talk about nanomaterials and future of battery storage. I will request our energy man, Mr. Pramod Deshpande, to introduce Amitej, and then Amitej can start his presentation. Over to Pramod ji.
Thank you. I am Dr. Pramod Deshpande. Today we have a speaker who is having at very young age a lot of innovations and credentials to his credit. He is an undergraduate from UDCT. Now it is called as ITC, Mumbai, Indian Chemical Technology Institute, which is a uh, deemed university and having a lot of history in chemicals and chemical engineering. He is postgraduated from the IIT Kanpur with MTech in chemical engineering. Then he has developed, he worked with companies like Deepak Fertilizers, Reliance. He is a recipient of Royal Academy of Engineering in terms of various funds and things. That he is also a recipient of National Energy Efficiency Award. His coming to his basic work, he generally the people don't go for a electrochemistry as a career. However, he is the person who has opted in his young age with a very different and difficult area of research, which is a electrochemistry, which is a interdisciplinary branch, and it has he has got a lot of interest in that, and he has developed a certain carbon nanotube material which has a lot of use in battery. It may be a liquid stage, solid stage, and that improves the performance of electrode, and that has resulted into what is lot of patents, and he is a co-inventor of number of products. On the basis of that, he is a material manufacturer as a startup located in Rajasthan, and basically original from Nagpur and studied in Bombay and Kanpur and settled in Rajasthan with a his startup. He will be explaining uh, what is the use of these nanomaterials in the battery and what he has achieved and what is the further future. Basically, today's focus is on along with the energy generation, energy storage, and where the battery plays a vital role. And battery, when the battery development takes place, the materials and the performance of the material and the electrode accounts for its efficiency, and that is what is the area in which he is working. Now I request uh, Amitej to go for his presentation.
Sure.
Amitej.
Yeah. Yes. Thanks so much, Dr. Pramod. Thank you so much, and thank you so much for the Tech Forum, and especially Dr. Mr. Vilas to giving me this opportunity to speak about this specific topic about materials in batteries and the usage of nanomaterials. So, me being coming from a chemical engineering background, for myself also, it was very new to get into batteries and energy storage because this wasn't taught during our bachelor's. But yeah, through experience and through working in the startup, like we've come to some material solutions for the batteries. I hope all can see my slide. Yes. Yeah.
Yes,
Okay.
everybody can see it.
Okay. So the today's topic, what I'll be talking about, would be the nanomaterials and the usage of it inside the batteries. Uh, Different chemistries from dominant chemistries today and the next generation systems, which is gonna come after say 5 to 10 years, and their use case inside different applications like mobility and grid storage and energy storage. So a background of mine is like as Dr. mentioned that I'm a chemical engineer, and right now I'm actually the founding member and head of product development at Cancrie. Cancrie is a nanomaterials company. It's a nanocarbon company. I've briefed about the company in the latest slides too. I'll come to that. Yeah. So today what we are going to cover is what is the current landscape, like what battery chemistries are we talking about today, and what materials are actually impacting the performance, different aspects of that materials, and what components of this the battery cell is the most important. And we'll also be talking about the emerging technologies like solid state batteries, sodium ion batteries, and their applications and the challenges in scaling these technologies and the nanomaterials impact. So this is going to be a very brief technical session, and I'll invite all the people to make it interactive. Yeah, you can stop me anytime and ask me questions. Yeah. So today, as we move ahead, everyone knows that batteries is the most hot topic as of now, and the reason for that is, yeah, we like as the whole United Nations and as countries, everyone has to achieve net zero goals, and to achieve those goals, two most important sectors where we need decarbonization is number one, the mobility sector, because automotive transportation sector accounts for second or third largest CO2 emissions in the world. And second is the power sector. Right now, people use coal and gas to convert like this heat into steam and then into electricity. So two of the major sectors which needs decarbonization is automotive sector, transportation sector, and the power generation sector. Now, where do the batteries come over here? So, like in general, batteries can be of two types. Number one is the primary battery. This is generally a non-rechargeable battery, which we all use in our remotes, TV remotes, or AC remotes. These are non-rechargeable. These extend the Duracell battery. These alkaline batteries, these extend for a lifetime, and these batteries do not need any recharging. So, and the second type of batteries is the secondary batteries, which we call as rechargeable batteries. These batteries can be recharged and charged again. Example, lead acid battery, lithium-ion battery, sodium-ion battery. These are the dominant chemistries out there in the usage, in the application side. So this presentation would focus on the secondary application, which is the rechargeable battery, not the primary battery. And why is it important is uh, primary batteries, they account for a lot of electronic wastage. So people are now shifting towards rechargeable batteries because it can be recharged and charged again and used again and again. So today, the dominant chemistries out there is lithium ion and the lead acid market. So lead acid battery as a market, the chemistry was established back in 1800s, and it's a very old chemistry where the anode part is the lead oxide and the cathode part is the pure lead, and we get a decent amount of energy output from it, and we get a decent amount of cycle life also. The second type of battery chemistry which is dominant today is the lithium ion market. You all know about it. The batteries that we use in our phones, in our laptops, and also in the EVs right now. And a lot of it is going for the grid storage also, the solar energy storage and the uh, wind energy storage. So that is the two major chemistries which are dominant as of now. Like 90% of the market share are covered by this. Other chemistries are there, nickel metal hydride batteries, but these are the two main dominant chemistries which capture the market. Now, what are the limitations of these chemistries? Number one, lithium ion energy density has plateaued in the range of 150 to 250 watt hour per kg. Like today, scientists and all the research organizations, they are striving to increase this energy density above 400 watt hour per kg. So we have different kind of innovations happening over there too. Second of all, in the anode side, there is a solid electrolyte interface, which actually limits the cycle life. I'll talk deeply about the chemistry sides in the upcoming slides. Second is, we all know that charging these batteries as of now is a hassle. It takes more than say 1 hour, 2 hours in general to charge a small two-wheeler battery. Uh, Now, if we have to replace petrol, in which we just need 2 minutes to just fill the tank and just run again, the competition is pretty high. We need to bring down the charging time from say 2 hours to say less than 10 minutes or less than 5 minutes. Then it becomes a solid competitor to the petrol or diesel vehicles. Second, like the last but not least is the cost. These batteries generally use critical materials like lithium, nickel, cobalt, As of now, the costs have fallen down because of the high usage, but also there is shortage from the supply chain side of things. So the material cost is rising up and up, and these are specifically concentrated in certain geographies, and the supply chain is a vulnerable issue as of now. So talking about the challenges, lithium-ion number one challenge, explosions that you heard. This is nothing but a thermal runaway happening inside a battery. And the reason for this is lithium-ion batteries use a liquid electrolyte, which is solvent based, ethylene carbonate and dimethyl carbonate. By its nature, these are highly flammable and volatile solvents. By default, if during say charging or discharging the temperature of the battery rises, these electrolyte, it catches fire and it leads to thermal runaway, and dealing with battery fires is a different ball game altogether. It cannot be dealt with a normal fire. Battery fires, you've all seen the videos. It is a chain reaction. It is kind of a runaway reaction. It exponentially it increases. Second, the supply chain is an issue, and also the electrolyte interface degradation, which causes the cycle life to go down. Talking about lead acid, solid chemistry, but it suffers from lower energy density due to a simple reason that the chemistry is not as advanced as lithium ion. It has a shorter life cycle as compared to lithium ion, but still it is able to provide certain applications which do not require that much amount of life. It is heavyweight, and the volumetric energy density is also very less. So this is a very good application. Lead acid, still all the automotive batteries that we use, all the say inverter batteries that we use as of now, it is used in telecom industry. It is used in say golf cart, forklifts, and all the stationary applications. This chemistry is still preferred. The reason is the lower dollar value. It's very cheap. And the most successful thing about lead acid is it's an established market as of now. And lead being a critical material, 90%, more than 95% of lead is actually recycled, and again it converts into this battery. So it is a very circular ecosystem with lead acid. Lithium ion yet to reach that level, but yeah, the technologies are getting developed to reach there. Then we have flow batteries, vanadium redox flow batteries. These systems, they use high energy pumps, pumping the electrolyte through the using of these pumps, and we need big storage containers. And again, these batteries again use vanadium, which again is a very critical material. It's not abundant in the nature. We also have nickel metal hydride. It suffers from its hysteresis effect, and it suffers from self discharge. So as of now, nickel metal hydride is not a contender for the applications like grid storage and EVs. So over here, these are certain challenges, but how can we address these challenges using materials? Because whatever, this is a electrochemical device, which means that the chemical energy is getting converted to electrical energy and vice versa during charging. So the chemicals usage and the materials going inside are the main crux of the energy providers. So we would need innovation, and we are doing innovation in materials to solve all these challenges. So how do we address this? So using nanomaterials, like using nano engineering at an atomic scale. Number one, using some advanced materials. In a battery, imagine that we have an electrode, right? In that electrode, there are certain electrochemical reactions which need to happen. Taking an example of say lithium-ion battery, on the anode, particularly people use graphite. Graphite, the reaction happening is the lithium intercalates between the layer of graphites. It goes and sits between the layers of graphite. Now, the amount of lithium ion stored will determine how much is the capacity of the battery, and the speed of this storage will determine the charging speed. So the anode materials and the cathode materials and the electrolyte materials have to be such that they have certain specific properties. When we talk about electrodes, number one, we need enhanced electrode conductivity, which is electronic conductivity and ionic conductivity. It also needs to be reduced internal resistance, which means when the reaction is happening, the kinetics should be much faster, and the temperature rise shouldn't be as much, because if the temperature rises, then there is a safety risk. So number two, the anodes, which is the most important part. Right now, in lithium-ion batteries, people have started using silicon carbon composites, and it's a silicon and porous carbon composites. As of now, graphite, the challenge with graphite is only able to provide, say, energy density of around, say, 200 to 250 watt hour per kg. But when we use silicon as an anode, it multiplies by 4 times. This is the amount of energy density it can store, because as chemistry, 6 atoms of carbon graphite, which is graphite, can store 1 lithium. But in silicon, 1 atom of silicon can store 4 atoms of lithium. The storage capacity is more. That's why the energy output would be more. So people have to, if we are aiming to go to that 500 watt hour per kg level, we have to shift to silicon based composites. But there are certain challenges in silicon too. What happens is, this silicon, during this charge discharge process, it suffers from a high volume expansion and contraction, which leads to mechanical degradation and the strength degradation. So we need certain materials which are porous in nature, which can act as a host to these silicon structures and minimize the risk of mechanical instability. Then we also have SEI, solid electrolyte interfaces. This happens on the interface of electrode and the electrolyte. And this again is a very important layer, because this is a protective layer for the electrodes, but it is a result of a parasitic reaction happening inside the battery. In general, the lithium is reacting with the solvent is an unwanted reaction, and that is what happens when the SEI layer is formed. It's an unwanted reaction, but it still is a protective layer. But excessive SEI interface formation would lead to capacity losses. So it has to be a balance, an optimized balance between the thickness of SEI layer and preventing degradation more and more. Number 4 is fast charging enablers. Like we mentioned that we need to replace petrol, right? So we need to have charging which can happen less than 10 minutes. So the porosity of electrodes is very important over here, which actually reduces the path length, the diffusion path length of the lithium into the anode material. So porosity is very important, but again, the trade-off should not be that there shouldn't be any more solid electrolyte interface formation, because it would lead to capacity loss, and by default the cyclic life would reduce. So these are the different trade-offs of how to use materials. It's a very delicate balance of material properties and their impact in the electrodes and their impact in the overall cell and the battery technology. So going forward, what advantage do we get through using these nanomaterials and all those things? 20% higher cyclic life gain. Imagine like a conventional EV gives a warranty of 5 years. Using nanomaterials, we can get 6 to 7 years easy warranty. And because of this, the total cost of ownership will go down, because the battery would now be running longer, right? So the vehicle life would by default increase. And mind you that today, all the EVs that we are running, 50 to 60% cost is just the battery cost for any electric vehicle. 50 to 60% is the battery cost. So battery is the main engine. It's the heart. So if we increase the cycle life, by default, the features, the power, the vehicle OEMs, they increase those features using just the innovations in the batteries. We also aim for resistance reduction by 40%. And why is this important? Again, because to stop the thermal runaways inside batteries, we need to minimize the risk of explosion, and we need to keep the temperature on the lower end. So we need materials, electrodes such that reduce the internal resistance of the battery. And it's a very simple test, which we call as electrochemical impedance spectroscopy, through which we understand what is the charge transfer resistance and all the resistance inside the electrode. We are aiming for more than 500 watt hour per kg potential of energy density. And how would that be possible? The current chemistry will not allow that to happen. So we need material innovation, as I mentioned, with silicon carbon composites and using solid electrolytes, shifting from the conventional liquid ones. We are aiming to get this 500 plus watt-hour per kg, which means the current range that you're getting out of your EVs, it is going to be double, just double. So imagine a vehicle where you get 2 years more life and double the mileage per charge, and all this with a cost reduction target, not at a premium price, but at a cost reduction target. So we need to aim right now $50 per kilowatt hour. As of now, the LFP batteries, they've reached a good $100 to $90 per kilowatt hour figure, and it is going to come down with scale. The best part about, as I was talking about lead acid sits anywhere between say 30 to 40 and $60 for the premium chemistries out there. Still, that's why lead acid is the most dominant and it's the most economical alternative as compared to lithium ion for applications where it can be replaced, not for applications like mobility and traction. So we need to scale the materials in such a way that it increases the energy density at very small dosing levels inside electrodes, but still keep the cost lower than $50 per kilowatt hour. So this is the challenge that we all have, and we all have to solve this through materials and design. It's an interdisciplinary sector, but through materials, as materials chemical engineers and as material scientists, we need to solve this issue through materials. So going ahead, what are the emerging battery technologies? Solid state batteries. What is it? It is nothing but a lithium-ion battery or any chemistry battery where the electrolyte is solid or semi-solid or gel type. Right now we are using liquid electrolytes. It's organic solvents, which is flammable again. So we need to replace those with say ceramic or polymer, quasi-polymer electrodes, which offer a lower weight, meaning that the energy density is going to increase, and also they provide lower flammability risk. So there is no flammable material inside. So the batteries would be safe. Already people, companies like say Toyota and BYD and Solid Power, they're targeting the commercializing of these batteries by 27 and 2030. So this is an upcoming thing. The only difference over here is the phase of the state of electrolyte. It's just solid other than liquid. Second is the sodium ion systems. We all know lithium supply chain is a vulnerable issue. Like we need to shift from say critical materials to materials which are abundant in the earth. Sodium is 200 times more abundant in the earth's crust as compared to lithium, and the cost is also very less. And as like India has a lot of reserves of sodium as compared to lithium. People have found out lithium ion reserves somewhere in Bangalore and somewhere in Jammu, but that is still in the exploration stage. Getting to that exact mining stage, it is going to take at least 20-25 years, and that is a long time for any battery chemistry to sustain, right? And we cannot be dependent on say, other countries like China, because 95% of all the battery materials, it is routing through China only. They own the mines. So we need to shift from chemistries which have more abundant materials. The only drawback with sodium ion is it has a lower energy density as compared to lithium ion, and this is because of the electropositivity of sodium. It is not a dominant chemistry as compared to lithium, but we can use it for specific applications like grid storage at entry level, and we can innovate on the energy density until it can be used for automotive and EV mobility applications also. So it uses cathodes of sodium vanadium phosphate, sodium iron phosphate, and it uses hard carbons as an anode material. Hard carbons, they're generally made with lignocellulosic biomasses, and converting them into specialized hard carbons which are battery grade. It requires a high amount of capex, high amount of tunability and customization, and it promotes fast charging, but it suffers from a lower coulombic efficiency if the quality is not up to grade. What does it mean, lower coulombic efficiency? It means how much energy you put inside the battery while charging and how much energy it gives out while discharging. So that percentage is very important, and it tells about how efficient is the reactions happening, the storage happening. So if we get a lower Coulombic efficiency, it does not solve the problem because the life would be lower. Third is lithium sulfur. Now sulfur is the most dominant, like it's talking about energy density. It is, say, more than 8 times the energy density as compared to the conventional batteries, lithium-ion batteries as of now. So this sulfur is again a very abundant material. This chemistry is where sulfur is used as a cathode material. Now using just sulfur during the discharge reaction, what happens is the sulfur gets changed. The structural changes happens when sulfur actually alloys with lithium, and it makes certain polysulfides. And these polysulfides are liquid in nature and they get dissolved in the electrolyte. And if they dissolve, then it is nothing but the loss of capacity. And these sulfides, polysulfides, they shuttle between the anode and the cathode. And this is a lithium is an active material. So we are losing all the lithium because it has converted now into some passive lithium polysulfides, which cannot be used for capacity. So we need to solve this problem with lithium sulfur, and nanostructured and nanocarbon hosts are the real game changer. People have researched about it for more than 10 years now. We need carbon hosts which can actually house these small sulfur particles to prevent the dissolution into electrolyte and prevent the polysulfide shuttling effect. But this is a chemistry, lithium sulfur is a chemistry which needs at least 5 to 7 years to come to a stage where it can be developed at a cylindrical commercial level. Scalability is still a challenge, but yeah, it is a chemistry where it can be used to replace aviation. So we all know that aviation is the most difficult to decarbonize industry. It still uses kerosene and jet fuel for running, and using batteries for aviation will not make sense because it will add on the payload as compared to the amount of energy it gives out. So we need such chemistries which have very lightweight but provide much higher energy. Lithium sulfur is that contender which can replace kerosene and jet fuel in the aviation industry. The real world applications, number one, we all know that it has to be to achieve the net zero goals, we need solar, we need wind. Due to the reason of, and these energy generation, solar and wind, it is very intermittent in nature. Solar, it only runs for say 8 hours in the morning, and in the night time it does not provide any electricity. So what is the solution? The solution is that we need to store the excess energy inside batteries and use it during the night time. So storage is important there to address the intermittency issue of these technologies, wind and solar. And these batteries, it needs to be in such a way that dollar per kilowatt hour should be lesser, and it provides a stable 4-hour duration storage. That is the normal storage that we need. Second application, electric mobility. Most important factor when it comes to mobility is energy density, charging speed, and safety. Safety being the most paramount factor over here, because if we provide with cells which are low quality, which do not have those kind of safety standards, it is going to result in catastrophes more and more, and it is going to result in lower adoption of EVs, and we are not able to solve our net zero goals by 2030 or 2047. Yeah. Challenge with all those things that we have as of now is Indian cell manufacturers. They're very concentrated. People are coming up now, but it is very concentrated as of now. And for localizing the cell production, as of now, what people do is a lot of people use the lithium-ion batteries, which people use in EVs and other storage things. They import the cells from other countries like China. They just assemble over here the cells into a battery pack and install a battery management system, and then just package and resale it. But the core technology still remains unaddressed, which is the cell. Cell still comes from outside. So we need to promote cell manufacturing here in India, and a lot of players like Exide, Amara and players like Ensure, a lot of big companies, they've come up to make the cell manufacturing here in India from scratch using the materials. So we need a mastery of battery grade material synthesis here in India, electrode coating, electrolyte formulation, and the cell assembly all over here. And then we have a thriving ecosystem to address the issues of integration of this renewable energy and the mobility. That is the main challenge, that we need to indigenize this manufacturing. And all of this using nanomaterials, it adds a bit of, sometimes the processing techniques with other nanomaterials, it's actually very complex. Scalability is an issue sometimes. Yeah, so challenge number one, scalability. Yeah, so lab scale, we all know that every day on lab level a lot of innovations happen, and these nanomaterials, they're actually difficult to produce consistently at ton scale level. Important parameters like process control, purity, and cost, they still remain a barrier to commercialize these materials. So what do we need is, we need extreme customization and extreme level of engineering to take this material from a lab scale to a pilot and then to a commercial scale, and all this within an acceptable cost range, so that we can make its adoption more easier and acceptable by the market without changing any processing lines. Another challenge is these chemistries, they still use critical materials, lithium, cobalt, nickel. They are not going to go anywhere because we depend on these materials for the chemistries, like even sodium ion, even for lithium sulfur, even for solid state, even for lithium ion. We have to be dependent on these materials because, and these materials are concentrated in very few geographies. Like, say, cobalt comes from a very small region of Congo Republic, and we've all heard certain atrocities happening with the laborers over there in the cobalt mining. Lithium, all the lithium mines, they're owned by China as of now, most of it. So all the materials, it routes through China to other countries. So we need supply chain resilience over there too. Safety and thermal management. So using nanomaterials in electrodes can increase the reactivity, which could change the C rate limits and the voltage limits. So we need customizations in the battery management systems too, so that we have a good thermal management and thermal interface between the user and the battery. Currently, lithium-ion batteries, the recycling infrastructure recovers 70 to 80% of all the critical materials, which is again a very good figure, given that we started with, say, 20%, say 10 years back. Right now, people use different routes like hydrometallurgical routes, which can recover this much amount of materials. Using pyrometallurgical routes, only like the yield is less than 40%. So that is not scalable at all. So herein comes the competition. Like taking a reference from lead acid batteries, 95%, actually 19 for the organized sector, 99% of the lead, which is the active material, is getting recycled. Lithium ion still suffers from a lower efficiency of recycling, which can cause a burden, because we need more and more materials now. More and more mining should happen. So this is a different sector, a different lane where the innovation should happen. Along with materials, we need another processing techniques in recyclings, and companies are doing that here in India, and we have a couple of peer startups to doing that. So what are the key takeaways? That materials are the lever. Like, we have to innovate inside batteries to address all the challenges using materials, and there is no single winner. It's a coexistence of batteries. Like, all the batteries, be it lead acid, be it lithium ion, sodium ion, anything, they will coexist. There's not going to be a single winner, and everyone will be suited to its own application based on its features it gives. So yeah, the selection of the battery chemistry for that specific application, it has to be driven by the use case. And again, we need to scale the ecosystem in such a way that we develop an indigenous capability of developing materials, developing cell production, developing BMS and recycling here in India. And then we have our goal of a whole battery ecosystem innovation by the next decade, using materials, using chemistry breakthroughs, uh, given that we're able to manufacture and integrate here in India. So this is the key takeaways. Now I'll just dive into what we do, like, as a startup. So Cancrie, like, our company's name is Cancrie. It's a nanomaterials company. It manufactures a new class of engineered nanocarbons, and we use lignocellulosic feedstock, right? As of now, a lot of these materials, they use fossil fuels like crude oil and coal to convert into nanocarbons and other type of carbons, right? Into carbon blacks specifically. That again accounts for more greenhouse gas emissions. So we need to use the current agricultural and the industrial wastage that happens and convert into upcycle it into the nanocarbons and then use it inside the batteries to get higher efficiency. So yeah, we are manufacturers of nanocarbons. We have our manufacturing plant here in Jaipur. These nanocarbons, these goes inside the cathodes and the anodes of the batteries, be it lead acid, be it lithium-ion, sodium-ion, and it provides a superior performance and a longer life and faster charging in the batteries too. Our main vision is making a sustainable energy transition. That's why we have chosen agricultural waste and industrial waste, not petroleum here. So we need a sustainable energy transition, and it provides higher efficiency, higher Coulombic efficiencies, and higher discharge rates using these nanocarbons. Our process is patented. We have actually 4 patents in this technology, from product, the process, and also the usage of it, the dosage of it inside the batteries. This is a glimpse of our manufacturing plant. Again, the challenge that I was talking about, uh, manufacturing it at a commercial level. We started at a very small batch, like say 1 gram batch, to now a scale of say 1 ton. So it has been a very like a learned, very challenging and a very learningful journey for us, uh, where we had to sit with the engineering guys, the vendors of equipments, and now we say that we've come to this plant after dedicating almost 3 years of our research and industrial scale research over here. And all the machines that you see over here are developed in India, customized in India, and are self-engineered. So we proudly say that we have achieved scalability of this nanocarbons that we are making using the ecosystem that we have in India and not depending on European or Japanese equipments. These The plant that we have is spread across 25,000 square feet, and we use all the state-of-the-art machines. And our plant is also authorized by Pollution Control Board (CPCBs) that we are using zero liquid discharge ETPs and the tertiary stage, like 3 stages scrubber that we use to maintain all the limits, the pollution, the whatever we the limits within of the CO2 or the CO and all the particulate matter are within the CPCB limits, and we've gotten the consent to establish and the consent to operate for this plant. So this was a big milestone for us, achieving this scalability and setting up our own manufacturing plant. This is the photos of our deployment of this nanocarbon going inside batteries. Now we have deployed more than say 2 lakh batteries in the market, and as we are speaking, we are talking to more and more people and commercializing it in different regions of India. We're exporting it to Oman, to USA. So we are trying to make a company here in India where the material is made here, but it is used outside. It's an export quality battery grade material, which is something which is counterintuitive, because people right now are using battery materials which are getting imported from outside European and Chinese countries. We are trying to create an ecosystem where we develop the material here in India, but we sell it outside. This is the thought process behind developing this material. This is some of the awards that we've gotten under this is the Bureau of Energy Efficiency. We were awarded National Energy Efficiency Innovation Award under the presence of Madam President. And yeah, with that, I would invite you all the people to join us in our journey. And any of you, if you want to have some high performing batteries on our developing in this ecosystem, please get in touch. I've This is my email ID and my phone number is over here. Yeah, so with that, I invite open the floor to questions, and if any discussion points we have. Thank you so much. Yeah.
Thank you, Amitej, for wonderful presentation. We really appreciate your efforts,
Yeah.
and we wish you all the best for your future.
Can you hear
Yes,
me?
yes, go ahead.
Yeah, yeah.
Yes.
Okay, this is Dr. Sanjeev Katti. Amitej, really very good talk.
Yeah.
Uh, I am also from ICT. I am actually a distinguished alumnus. I have my own startup in Pune.
Oh,
We
nice.
are working on membranes for
Okay.
hydrogen and so on. But I think you had a really good talk on this one.
Yeah, thank you so much.
I would like your perspective a little bit more on the vanadium redox flow batteries, because
Yeah,
India's first vanadium battery project I started in IIT Madras, and with high energy batteries HEB, and
yeah,
now they are in the pilot and further phase. Uh, I think you mentioned it's the vanadium that is not available, or what are the issues with the materials from that? Because I think we are getting very good results from vanadium. And as you know, the stationary batteries versus flow batteries, I think overall, over time, flow batteries should take off. We
correct.
have also sponsored some work on iron flow batteries as well, because that is also double this thing. So, since you have more perspective on this one, please let me know first, effect, what is the future of flow batteries? What do you think? The
Yeah,
overall market, it may take time, but that seems to be, you are separating the capacity and how long you can run.
yeah.
That is number one. So first question is, where do you see flow batteries in general and so forth? Number two, what is the vanadium supply and so on situation, and then I'll give you my perspective as well. And
Sure.
then third, who is exactly buying your nanocarbon material for batteries? Because it sounds strange that we have so many battery manufacturers who are importing this today, versus
Yeah,
you are trying to sell it outside, and maybe from there it will come back. We are at our end also are finding the same thing. We are going to introduce our product first in outside in Europe and US, and then bring it back over here.
got
Thank
it.
you.
Yeah, yeah. Thanks so much, Sanjeev ji. Nice to know that a fellow ICTN in the talk. Always nice to interact with ICTNs. Yeah, talking about the first question. Yeah, redox flow battery, vanadium redox flow battery. I definitely see like it is gonna be a coexisting system, but for grid scale storage, not for mobility applications. I feel that vanadium redox flow battery is a best contender for the grid scale and more than megawatt or like megawatt storage applications. Say more than 5 megawatt or 10 megawatts. That's where the real beauty of this redox flow battery would come. And in spite of a higher upfront dollar per kilowatt hour is something which I saw through the industry, but the main crux is the higher life cycle, right? As compared to lithium-ion alternatives, redox flow batteries is a much it's a much sturdy chemistry in terms of cyclic life. So the total lifetime cost of storage, the LCOS would be much lesser with redox flow battery for sure. And I specifically for the storage applications, mobility applications, yeah, as we all know that this is a very bulky system as of now, which cannot be integrated into a small volume based systems like say mobility, a car hatchback, right? We need systems which have a very low volumetric energy density. So I still feel that it has a very good future, and it is gonna be the next contender. It is the contender for the grid scale storage at higher megawatt levels. And there are a couple of companies like vflow tech. They are developing this vanadium redox flow battery, and they've deployed a lot of grid scale storage in different countries like Africa and other countries. So this is with redox flow battery. Talking about the material angle of this redox flow battery, vanadium is something like again it's a critical, it's not a abundant material, but it's still the processing can happen, then the recycling can happen. I would say that it's not just vanadium, it's the whole membrane electrode assembly, right? We use MEAs over there too, the membranes. Currently, the topmost company to manufacture membranes is like the technology was licensed from DuPont, right? It was Chemours is the
Hmm.
company. They use Nafion, right? You would be aware of Nafion. So and the MEAs, which is the membrane electrode assembly, they use certain gas diffusion electrodes. Then there is membrane porous electrodes, and then we have different bipolar plates also. The whole, it's not just the vanadium material, but the whole components of the flow battery, which I feel it needs to be, it's still in the hands of certain few here, like in the world, like big companies. So as of now, I know a couple of startups in Bangalore who actually are manufacturing membranes from for redox flow batteries. They also manufacture gas diffusion electrodes. So they are upcoming, and they're challenging that DuPont company, the Chemours company, that they are replacing Nafion with their own membranes. So talking about materials, it's not just vanadium. Vanadium is a critical material, and you would know better about it, Sanjeev ji. But from my point of view, it's the whole component, the not just the electrolyte, it's the whole component that we're trying to use over here. And the third point, answering, so our nanocarbons that we manufacture, we sell it to all the cell manufacturers and the battery manufacturers in India, and in the outside Oman. We are selling it to lead acid battery manufacturers for the negative plates, and we increase the life by 20%, increase the charging speed by 2 times, and reduce the warranty returns. It's been 1.5 years in the market now, and we've sold the nanocarbon worth more than 2 lakh batteries. And as we are speaking, we are deploying the technology to more and more customers and more users of these batteries. And lithium ion is also something that we've made the product for lithium ion also, and we are doing industrial scale pilots and trials with the commercial Indian cell manufacturers out there, which are very few, you would know, which are very concentrated and very few. But we are in touch with a couple of them, and we are doing commercial industrial grade trials with them. We have already developed the material at a lab scale and at a pilot scale, but right now the transition is happening from a pilot scale to a industrial level lithium ion cell. And we claim that with using our material, you'll get a better range, better energy density, and a better cyclic life in small certain dosing percentage. Yeah.
Well,
This
thank you for your perspective. I will get back in touch with you for
Sure,
some
please.
other things. I think
Shall we
uh,
have next question?
Please, yeah, please, Sanjeev ji, you can get in touch, please. Yeah, thank you.
uh, Napion means you are saying nano, this ion exchange membranes,
Yeah. It's an ion exchange membrane, Pramod ji. Yes.
both anion cation,
Yeah. No, it's actually the protons. Like when we talk
proton.
about
Okay. So only that membrane they are making, not
membranes,
both the
they're
type.
giving. Hi, they have the monopoly of this membrane. The company
No,
called
it has a lot of
Chemours.
application for electrodialysis. And that
Ah,
is the reason I just asked. Anyway, please.
yeah. It is actually used in the fuel cells also, like hydrogen economy, green
Yes.
hydrogen, electrolyzers, and fuel cell. It is used in that ecosystem.
Yeah, I understand.
Yeah.
Okay, shall we have next question from the audience?
This is Amit Borkar from Pune.
Yeah.
Amitej, my question is how long it will take India to be self-sustainable in this journey?
Yeah. Yeah. Amiji, thanks so much for the question. For the self-sustenance of India in this specific area, which is batteries, I mentioned in my slide also, like we need a wholesome ecosystem over here where we can only be self-reliant when we have the control of the materials too. Just to give you a perspective, as I mentioned that 90 to 95% of the materials it is getting imported from China here in India. People are just assembling here and they're just reselling it. What we want to do is we want to create and manufacture here in India using abundant sources and upcycling it into making a premium grade, premium battery grade product, and then supplying it to a Indian cell manufacturer who is using materials. So the ecosystem, what we have in our mind is how India can be self-reliant in this sector, having materials made here in India which are scalable. And scalability can only be solved when the machines that you're using are also self-engineered and customized over here. And so that's where the equipment manufacturers, the engineers, their expertise comes in mind, because they need to develop equipments the technology in such a way that it can help battery grade material production. And battery grade material is a very tricky thing, because we are talking the impurity levels in ppms, part per millions. So because any impurity inside a battery would lead to any parasitic reaction, any short circuit, and a loss in conductivity. So it has to be battery grade material. So it has to be a synergy of the material manufacturers, the vendors, equipment vendors, the cell manufacturers who are indigenized, who are based out of India. And after we make these cells, then the cell is the main heart of any battery, and then we can actually export this cell to the outer countries also, and use these cells for our internal usage in EVs and for grid storage also. So this is a vision where we can create a uh, wholly indigenous ecosystem for battery technologies. And also we need research institutes which can spearhead technologies that they're developing, and faster commercialization to from that lab scale to a commercial scale. So academia is a major role, and we have been developing the product and our company through collaboration with a lot of academias, right? And that's where the research happens. And the startups like us, and say companies like big companies, they are the executors. So we need to execute from the lab scale and take it to a commercial stage, and then validate the technology. So this is the idea behind it.
Okay, great. Thanks, Amitej ji.
Yeah,
Thanks.
yeah, yeah. Thank you.
Yeah. So shall we have another question? Anyone from the audience? If there are no questions, we can close today's Tech Talk. So Amitji, thank you very much for this wonderful Tech Talk. And I must thank the audience for a very good interaction, especially Dr. Sanjeev Katti, which made the discussions interesting. There are, of course, a lot of Chupa Rustums must be there who just wanted to contact Amitji later. But definitely, I can say it was a wonderful presentation, Amit, and we really appreciate your efforts and wish you all the best in your endeavor. We will have two tech talks next month. First one is on 14th, which is by Samir Bhagwat. He will be talking on nanotechnology, focusing on lubricants. And Vinod Joshi on 21st, he will be talking about the product development. So I will announce the details in the due course. So thank you, Amit ji, and audience for this interactive session today. And we will meet on 14th of this month. We
Yeah.
close and say thank you to everybody.
Thank you so much, Vilaji. Thank you so much for providing the opportunity, and thank you, audience, for listening to me and having such a wonderful interaction. Again, thanks so much, Dr. Pramod and Mr. Vilas and the organization committee for giving me the opportunity to present this technology. Thank you so much.
Okay,
Looking
Pramod
forward
ji,
to
would
the
you like
future
to say
connections.
something?
Thank you.
Pramod ji, would you like to say something?
Yeah, here's one of the intention is that can certain academic institute, including Pune University, come forward for his research ideas and support him? Am I right, Amit?
Yeah.
Amit J? Yeah.
Yeah, yeah, yeah.
Because
Yes, yes, yes.
there are good organizations and educational institute, even the private institute who wants to go with the innovations and things like that. There he can support the research. That is what is the discussion I had with him in terms of ideas and concepts, where the young guys can come up over, and there are institutes who are offering chemistry post graduations and other chemical engineering graduations and other things, where people can offer his ideas as their research project. That is
Right.
what I will say. And
Yeah.
he is ready to interact for those initiatives.
Yeah.
Or they can contact me. We can work together. No issues.
That's great. That's great. This was not known better. You said it,
Yeah.
Moji.
So those
Definitely
members who are
spread a word.
present can promote that idea with those who are associated with academia, and can we can work out something.
This
Yeah.
is a specialized area. Definitely, Pune is a resource center for such activities. Definitely we will spread a word. Of course, this recording will go to many, and we will make sure that this activity grows. Thank you all,
Yeah.
and we announce the today's Tech Talk is over.